Hello everybody, my name is Koklikyo and I'd like to tell you about this program that I've created. As you can see, it's a simulation of our solar system, so we've got planets orbiting around the Sun. And you can see a lot of information on the screen, and I will describe what each of these buttons do later in the video. After that, I'd like to mention briefly what methods I'm using to calculate the motion, and after the methods, we will go through the code very briefly and I will tell you what parts of the code does what. We are going to start with this largest screen where we can see the planets themselves. If you click on a planet, it will show its name and it will show more information about it here. You can see that the scale is given in astronomical units, and in the upper left corner you can see the date of the simulation. That's probably all that you can control from this window, so we will move to the camera. You can zoom in and out, and you can change the camera's position. Then you can change some basic inputs for the computation. Epsilon is basically how much time it passes between individual steps in the computation. But you don't really need to worry about that. And then you can set the speed of the computation, and if you click the start button, it will start calculation. Then we've got the panel here, where we see most of the information about the planets. So we can uncheck this checkbox, show info, and it will hide this information, but it will still show the trajectory of planets. Then we can see the planet's name, and if we uncheck this checkbox, it will stop showing the planet's trajectory. And if we check it again, it will start showing it again. Then we can check prediction, and it will show predicted trajectory for the planet. However, you will not be able to use it in every case, only when the planet is in orbit of the Sun. And we will see that doesn't have to be true in every case. I will explain apply force a little bit later because it's a little bit more complicated. Then we can see the planet's position, x, y, z components, and r is not distance from the origin, but it's distance from the Sun. It's a little bit different because the Sun itself has a distance from the origin. A small one, but it does. Then we've got the planet's velocity, obviously here, and its speed. We can also see the net force acting on the planet, but it's useful only, it's important only for the calculation and not for a viewer. So we don't need to worry about the force. If you click more information, it will display more information. And these three values are connected to the prediction. The A is semi-major axis of this predicted ellipse. B is semi-minor axis of this ellipse, and E is eccentricity of the ellipse. Eccentricity basically tells you how much elliptical the trajectory really is. And if it's close to zero, it tells you that the trajectory is almost a circle. Then we can see the mechanical energy of the planet, which is sum of its kinetic energy and its gravitational potential energy. We can see that the gravitational potential energy is negative, but it's just a convention and you don't need to worry about it if you don't already know it. What's more interesting is the escape velocity. This is the speed that if the planet reaches it, it leaves the sun's gravitational influence, and I will hopefully show it later in the video. Then we've got mass of the planet and its orbit period. And I should also mention that you can change the speed and the position of the planet. So for example, I will change the planet's speed so that it's greater than its escape velocity, and what it should do is that the planet should leave the sun's gravitational influence. So hopefully we will see that. And we can see that the Earth is moving out and it's not going back. And we can see that its speed is greater than the escape velocity, so it will not come back ever. I will just reset the calculation. You can add an object, you need to name it, and you need to give it initial position and initial velocity. So I will give it similar values to the Earth's ones. And after we click Start, the object will appear in the simulation and it will account for it. Okay, so now I will explain the Apply Force button. If you click on it, you will start applying force on the planet. You can choose the direction of the force. The direction of motion is direction of the planet's velocity. From the sun is direction away from the sun, and general direction is just direction of the x, y, or z axis. So I will choose the direction of motion, and deviation um, is how much it deviates from the direction you've chosen. So I will set it to 0, which means that it will be precisely the direction of motion without any deviation. Then you need to choose the size or the thrust, which is the size of the force you will apply. I will choose a similar force to the net force acting on the planet, and then you need to choose a fuel, which is um, which is the fuel which you will burn to produce the thrust. So for example, I will give it like something like this, and consumption of the fuel is given in kilograms per second. After you click confirm, it will start applying the force when you start the computation. And if we click prediction, we can see how the prediction is updating and the ellipse is growing. And actually, we've given it enough thrust so that the Earth reached its escape velocity, and again it will leave the sun's influence now. And that's probably all you need to know about the controls of this program. Also, I should mention that you can play with it on my website, and I will put a link in the description, but you can also download it if you click save page as, and you will save it somewhere on your computer. It's a single file, so you shouldn't have a problem with it. We'll replace it, and we can see that if we open the program in our web browser, it's the same thing. So that's it for controls. Now, I'd like to tell you more about the methods which I'm using to calculate the planet's motion. And I'm using a method described by Feynman in his lectures, more precisely in his 9th lecture called the Newton's Laws of Dynamics. And you can read it online for free. I will put link in the description. And if you don't know who Feynman was, so he was basically a very famous physicist who knew how to explain physics very well, and he won a Nobel Prize for it. Not for it, but for physics. Um, so again, I don't think that I would be able to explain it better than him. So you can check this link out if you want to understand the method which I'm using to calculate the motion of planets. Officially, this method is called the Euler method, but Feynman doesn't use the basic Euler method, but he uses a modified version. So you can find more information here. This method is very simple, but we can use it in our example when we've got planets orbiting at the set distance, but you cannot use it all the time. For example, if you have an object which is moving close to the sun and then very far away from the sun, so the distance between the object and the sun is changing dramatically, you should use different method because the Euler one is not very good. So for example, you can use the Ranch-Kata methods. So you can read more about it here. But what all these methods have in common is that you need the initial positions and velocities of the planets. And I got this information on this website governed by NASA. And if you set this to vectors, here you choose your target body, and here you choose the type of the coordinate system that you want to use. So I've chosen the origin in the solar system barycenter, and here you choose the time of the data. And if you click generate the data, here under results, these constants are not important for us. So here under results, you can see the position of the object, xyz, given in astronomical units. And under it, you can see its position, its velocity, and you can see the individual components, so x, y, z velocity, given in astronomical unit per day. And that's all you need to know about the methods. Finally, I will go through the code and I will tell you about its different parts. So I've got everything in one file, and I know that it's usually not a good idea to do that, but I had to do so because I had to give this file to my teachers, and I know that if I gave them 5 different files, they would lose 4 of them and it wouldn't run properly. So we are stuck with one file, and I'm too lazy to overwork it. So we've got some style, so CSS, a lot of CSS for style. Then we've got HTML itself, so canvas, and controls, so camera, computation, and other. Then I declare some variables, and this code here, it adjusts the size of the canvas and the controls. Then I declare more variables. Here is the place where I input the initial positions and velocities. So we see Sun, Mercury, Venus, Earth, and so on. More variables here. I'm already counting I already do initial calculations which I need to do before I can start a loop. Then this piece of code takes care of the clicking. So when you click on the planet, it will describe, it will display more information. And here I call the first animation frame. Each other animation frame I call inside the function draw. So more variables, more variables, more variables, and here is the function draw. So what the function does is that it calculates the new position and then it draws the new position on the canvas. So here is the start of the calculation. It goes on, and here is the end of the calculation. After that, it's just drawing on canvas. And by the end of the function draw, I update this camera position and camera values. And then I call another animation frame. And here the function draw ends. After the function draw, I've got just a bunch of helpful functions to help me count with vectors. So for example, I know that I've got defined functions for dot product between two vectors, vector length, vector addition, and so on. I've got also vectors for creating planet div, which creates which displays more info about the planet when you click on it. I also have function update planet div here, which updates the function, updates the info. I've got functions for applying the force, creating a new object, etc. And it's all down here. But they are not that important anymore. Yeah. And I end with hello world. So yeah, that's all you need to know about this program which I've created. I hope that you've learned something from it. Maybe you use it or you add something interesting to it. And yeah, that's all from me. Bye.